Alright, so today we are going to be talking about Chapter 12, which is a very interesting section of chemistry that is really fun to think about, a little bit challenging mathematically wise, so for those of you who are really good at math, this is going to be kind of like your area to shine. But it is the rate law. Okay, and it is an offshoot of what we've already looked at. We've looked at how an atom is put together, right? We have our Lewis dot structures. We've looked at the stoichiometry, how many of everything. Now the last piece of the puzzle is the rate. How fast is the reaction going to take place? Is it going to be an infinitely slow one? Is it going to be an instantaneous reaction? That is what the rate law is going to tell us. It's really important because if we do have a reaction that is going very, very slowly, we can try to find out what step that slowness is at and speed it up. Or if it's going very quickly, we can try to slow it down once we know this. So we're going to have to introduce a few concepts. I'm going to be working directly from the book, so if you've got your book out while you're watching this, that will help you out a whole bunch. Reaction rates, 12.1. The equation that they're going to start out using is nitrogen dioxide decomposes into nitric oxide and oxygen gas. Okay, we've got everything balanced there, and you can draw the Lewis structures for all these things and all that stuff. But now we want to know how fast is this reaction going to happen? What's going to occur there? To do this, we have to make sure that we understand a couple of things. So just a quick review. Everything on this side of my arrow is my reactants. Everything on this side of my arrow is my products. Okay, for the rate of the reaction to start out with, we're only going to be worrying about my reactants. Alright, and so for the rate, what we are going to say is that it is going to be equal to the concentration of whatever I'm looking at, so in this case of NO2, at one time minus the concentration of NO2 at another time. And we're going to divide that, okay, because it's a rate, so it's going to be an amount over time, by the time that we start to the time that we end. Or rather, the time we end to the time we start, so T2 minus T1. All right? When we write this, because that was really, really hard to write out, we can shorten it a whole bunch. First off, we can say that concentration, we're just going to use these brackets for. So the concentration of N2 at T2, at whatever time we end at, minus the concentration of my reactant at whatever time I start at, over the time I start, the amount of time that's gone by. And we can even make this simpler. Okay, so this is just a lot of annotation. It's not really chemistry going on here, just so that when I write it up on the board, you know what I'm writing. Or when you see it in a problem on the test. We can say the change, remember that this triangle thing means the change in the concentration of NO2 over the change in time. Okay, so we can write this really, really simply from that really long equation that we saw earlier. All right, so on the next page there, they've got the graph of this shown. So what they did is they said we're going to go from, the two times that we're going to look at is 50 seconds. So that'll be time 2, that's when we're ending. And time 1 will be at 0 seconds. So right when I start, and then we're going to go to 50 seconds. So we have to get on that graph. We look at what the concentration of the NO2 is, or how much of it is in that volume at those two times. And we find out that it is 0.0079 molar minus 0.0100 molar over 50 seconds. Okay, we do that math and we come out with negative 0.42 times 10 to the negative 5 molar over seconds. Okay, and they kept it moles over liters times seconds. Either one is the exact same thing. Well, now this is what we would expect because the NO2 is decreasing, right? And the NO and the O2 is increasing. Well, it gets kind of messy to have those negatives in there. So when they set this up, the general rate law that they're going to throw a negative in front of that to get rid of that negative. Because we know that it should be a negative. Because we know that it should be going down. So my answer to this then is going to be 4.2 times 10 to the negative 5 molar over seconds. Okay? All right, so for the first 50 seconds, this is the rate. Now that rate is not going to remain constant. It will change as the amounts of the products and the reactants change, and we'll look at that in more detail later. But for those first 50 seconds, that's what the rate is. They've got a little table there that shows you what the rate of the reaction changes to. You can do the instantaneous rate of reaction if you know calculus. So since we don't all know calculus, I'm not going to focus too much about that. But for those of you who have done calculus, you can see how you would get the instantaneous rate of reaction there. And just by finding your derivative of that curve, an instantaneous point on that line would give you that. We can also look here, so switching gears now away from calculus a little bit, we can also look at the rate of the reaction in terms of the products instead of those of the reactants. And it's just set up the exact same way. There's nothing really too different about it, but we do have to look at one thing really quick here. Here's our equation again. If we notice stoichiometrically, this 2 nitric oxides are used to produce 1 oxygen atom. So when we set up our equation, we saw that the rate for NO2 was going to be negative the concentration of NO2, the change of concentration of NO2, and the change of time. Well, when we do this for the product, if we do nitric oxide, it's going to be the exact same thing. Okay, so the concentration of NO, remember those brackets mean the concentration of NO. And we would expect this sign to be negative again now because it would be positive because we're increasing, but then we threw the negative on there, so it's going to be, yeah, it's backwards. I know everything in chemistry is backwards. But these two should be the exact same, right? Because for every 2 of these that are destroyed, 2 of these are produced. So we would see the exact same, and you look at the slope there, and it's just inverted. For the oxygen, however, the rate of the production of O2, we have to keep in mind that it is at a rate of 2 to 1. So we would have to times it by 2, and then we would see that same curve there. All right, so that is 12.1.